So, way to resume our discussion about logic. We're going to extend this so that we can understand, at least understand the fundamentals of probability. For this, I'm going to introduce you now some new concepts. These are going to be, of course, very closely related to what we have been discussing so far. The first thing is deductive and plausible reasoning. And by the way, I am following now a book by Jaynes. Jaynes, I got right the name here. Jaynes, one of his books. So we're going to be discussing about deductive and plausible, that's supposed to be a plausible reasoning. And I want to start with a very general discussion about this concept. Now, I'm not making this up. I am actually stealing this directly from a Jaynes book. This is the genitive, the Anglo-Saxon genitive. And because it's a very good example, and it conveys very well what I'm going to introduce later, the concept that we will develop later. Now, again, this is an extension of the introduction to mathematical logic, and the aim here is to end up with machinery that allows you to understand how to compute probabilities. The final goal, of course, is to use all of this so that you can understand what quantum mechanics is actually doing, so that we first have to go through all of this. Now, again, this is a summary of a couple of lectures that I have given to some students who want me to make a summary. So, now, just picture the following situation. It's dark night, and a policeman is walking down the street, completely empty. And at some point, this policeman discovers a shop, and that shop has a broken window. Everything is full with broken glasses here and there. And from this sea of broken glasses, a gentleman emerges. Somebody, a gentleman, wearing a mask, a black mask, and on his right hand, because he's right-handed, he's holding a bag. That policeman crosses the street, goes to this man, talks to him, asks him to show what's in the bag, and surprise, surprise, the bag is full with jewelry. Now, the policeman at that point, makes a decision. This person is dishonest, not at the level of a bank entity, but at some point, at some level, this person is a dishonest citizen. Now, the question is, what reasoning, what process is going on in the head of this policeman so that he can get to that conclusion? Okay. The first thing that should come to your mind is that, one, this was not a logical deduction. Okay, I apologize for my writing, but this is what it is. You know, it could be that this gentleman is actually the owner of that shop, and as he was walking back home from a party where, you know, you have to wear masks, etc., by whatever reason, imagine, because, well, this happened to me once, that a car was, you know, passing by very close to me, and there was a small piece, a pebble, a small piece of rock on the street. That car pressed that small piece of rock, and that thing got a slingshot in my direction and almost hit me when I was a boy. I still remember the noise that it made when it hit the wall. Now, it could have been the same thing, right? Could have been that a car had pressed a rock, a small piece of rock, in such a way that it had been hit the glass of the shop, and that glass has been broken. So, while that gentleman wearing a mask is the owner of the shop, the policeman is getting to the, in quotation marks, conclusion that he's stealing from that shop, whilst what in fact this poor man, what he's doing is to try to rescue his property. Okay, so the evidence did not make the gentleman's dishonesty certain, because these are two different things. So the evidence was not a proof that he was dishonest. We did not have the certainty. It was not certain, but it was plausible. Okay, it was not certain, but it was plausible. Now, why was it plausible? So, this is a very good example, and that's the reason why I'm stealing it, of a kind of reasoning in which all of us are experts, and we're actually using this on a daily basis. I see that the weather's cloudy, and therefore it's going to rain, or it's very likely that it's going to rain. But if you examine the facts, you will very soon realize that you do not have enough information to achieve that conclusion. Now, this is a very complex problem that spans over 24 centuries, and it needs to be still worked out, but to what degree, well, it depends on what you define as a common sense, because anybody would say it is of common sense that that gentleman wearing a mask is still in the shop. Okay. So, as usual, all discussions related to these questions go back to ancient Greece. You know that they have a weak point, a weak whatever, soft spot for ancient Greece. Deductive reasoning and plausible reasoning. It goes back actually to the organon of Aristotle, Aristotle, I don't know how to pronounce it in English, but I don't care much because it's not an English word. In his work, of course, what I'm going to explain now is an oversimplification of what you can find there. There are two different ways of analyzing this problem. We will start with apodeixis, and I have this urge of writing the word in Greek. Apodeixis, there's an accent here, apodeixis, which would be transliterated as apodeixis, because this I here is not pronounced. EI are pronounced as an E. Apodeixis would be with the tone apodeixis, but anyway, sorry about that. Deductive reasoning, this thing here, can be analyzed into the repeated application of two strong syllogisms. If A is true, period, then B is true. This looks extremely simple at first glance, right? Another way of looking at this is the following. A is true, and I cannot insist enough upon this. This is a copycat of Jaynes' book, what I'm doing now. A is true, with some personal comments, additional examples, and at some point I will probably use a different text. But I find these first pages extremely interesting and very pedagogical. Anyway, A is true, therefore B is true, right? Now, this is the dream of a mathematician and of basically every human being who wants to solve a problem. If you come up with a situation in which you can propose a statement like this, things get very easy. Now, what would be the contrary of this? Well, remember, the initial syllogism is this one. If A is true, then B is true. I will work on my writing, I promise. Now, the inverse of what we have seen before is the following. B is false, therefore A is false. Okay? Now, this is what we would like to use. I have to mute here something because there is a noise. Okay, there we go. Sorry about that. So this is the kind of reasoning you would like to use all of the time, because it is easy, it is strong, and we understand it very easily. Now, in real life, however, before you come to this kind of strong syllogisms, remember, A is true. Therefore, I'm going to note it like this because otherwise it's going to be very boring for me. Therefore, B is true. In nature, in reality, you don't have this kind of strong syllogisms, which are ideal. The process which leads you to find and prove a theorem about something in mathematics quite frequently, and I am almost tempted to say in 100% of the time, is not one of these strong syllogisms, but it relies on a weaker version of it, something which we call a weaker syllogism, or using the ancient Greek word and hypagoge, which is written like this. With an accent here. Hypagoge. I know that modern Greeks will criticize me, but in ancient Greek the sounds, so the letters E, A, E, and E sounded all of them differently. In modern Greek, all of this is an E, I know that, but in ancient Greek they are different, and here are tones like Chinese. So this is an hypagoge. Anyway, the transliteration would be, of course, hypagoge, like this. So in real life, we rely on weaker syllogisms. For instance, so look at this. If A is true, then B is true. So B is true, therefore A becomes more plausible. Now, in going back to the initial example provided by Jaynes, because we do see a man wearing a mask crawling out of a broken window from a shop with jewelry in a bag, it is more and more plausible that he has thrown the stone into the glass in order to rob what was in the shop. Now, the evidence, what you see, is not proving that A is true. But, on the other hand, we can come to a conclusion. So, sorry about that, again I got distracted. Too much internet, too many programs sending notifications and these things. So, the evidence is not proving that this gentleman is dishonest, but when you analyze one of its consequences, you become more and more confident in A, in the truth of A. Okay? Let's look at a different scenario. Now, I'm going to write down two propositions. By the way, I'm going to be using capital letters for propositions. And proposition A is going to be the following. It will start to rain by 10 a.m. Okay? So A is going to be start rain by 10 a.m. the latest. And B, a different statement, is that the sky will be gray before 10 a.m. Sky cloudy before, that's important, 10 a.m. Okay? So, if you observe clouds at 9:45 a.m., does not imply that A is going to be true. So if you observe at 9:45 that the sky is getting gray, you see a lot of clouds, etc., this does not imply, a fortiori that you will have rain 100% sure at 10. But we have this thing called common sense. And common sense follows the weak syllogism, hypagoge, if you remember. And you might take an umbrella because it is very likely that it's going to rain. So you behave as if you were completely sure that it's going to rain. Now, as you can see, this is not true, but you change your behavior based on an hypagoge, a weak syllogism. Now, when you write if A, then B, the only thing that you are saying is that B is being expressed as a logical consequence of A, but not as a causal physical consequence, which could be much later, at 11 a.m., at 13 a.m., or at 16 a.m. The rain at 10 a.m. is not the physical cause of the clouds at, say, 9:55 a.m. Okay? So, what I'm saying is that the proper logical connection is not in the direction of the uncertain causality. So, saying clouds, therefore rain, is causal but uncertain, and saying rain, therefore clouds, is certain, but it is non-causal. So this last one is certain, but non-causal. Now, this might look trivial to you, but I have seen, yes, I'm going to say it, I have seen a plethora of papers being wrong because of this kind of misclassification or interpretation of causality. Okay. Now, let's move on. Now, I'm going to talk about another weak syllogism. Okay, so another weak syllogism. Okay, let's remove this. And again, remember, if, sorry, this is the contrary. Sometimes I write fast, I think faster than I write. If A is true, then B is true. Okay? Now, look at this. A is false. Therefore, B becomes more plausible. Now, the evidence does not prove that B is false, but one of the possible reasons for its being true has been eliminated, and therefore we feel less and less confident about B. When a scientist is working on a theory, experiment, whatever, this is the kind of syllogism that he's using. Now, the reasoning of the policeman does not belong to any of the above types. It is led or described by an even weaker syllogism. So again, this is our departing point. If A is true, then B is true. But what is going on in the head of that policeman is the following. B is true, therefore A becomes more plausible, right? Now, what is going on here? All of this sounds like a very nice and fancy way of, performing dissection, maybe even a vivid dissection of the first scenario that I described. But then you could argue, come on, Pau, you see a broken glass, you see a guy emerging out of that window with a bag full with jewelry, wearing a mask. What are you talking about? It is quite clear that this guy is a thief, right? This is what, this is how you could protest. So what is going on here is something deeper and much more complex. Even if you do not realize it, what you are doing is to use prior information which you might have stored in your head. For instance, the plausibility that it rains at exactly 10 a.m. depends on the color of those clouds. If it's extremely dark, it is very likely, right? But if you see a white, gentle cloud at 9:45, well, it could rain, but it doesn't look like that. Now, what would happen if every single night that policeman walking down the street witnessed a very similar situation? A guy wearing a dark mask, a black mask, getting out of a window because for whatever reason, the street is full with people, and those people are getting squeezed by cars, and the cars are broken glasses, and the owner of those glasses, of those shops, and the glasses as well, feel like rescuing their properties. Well, at some point, that policeman would classify and identify that situation as something usual, something normal, and not at all suspicious. Right? Very soon, that policeman would just ignore that thing. Now, this is why you are relying a lot on prior information to evaluate the problem, the plausibility in a new problem. And this is what we call common sense? Probably because it is very difficult to describe what is common sense. Now, all of this is a kind of introduction to plausible reasoning. If you are interested in these kind of things, you should look at Polya's work. It's actually 3 books, which is what similarly Jaynes is using for his work, and he himself points to these books, which are very nice. Now, when you are facing a theorem and the proof of that theorem, well, a theorem has a proof anyway, otherwise it's a conjecture. You are presented with the end result, and mathematicians really try very hard to come up with an argument which uses the strong syllogism, if you remember, the apodexis, right? Apodexis. But in the way to that strong syllogism, that mathematician very, very likely, and again this is a syllogism, very likely has strongly relied on very weak forms of syllogisms. So, hypagogae, okay, in this case it would be hypagogae, so plural. Anyway, yeah, and then, and by the way, Jaynes in his book mentions a quote by Banach, in which he says that good mathematicians see analogies between theorems, great mathematicians see analogies between analogies. Okay. Now, all of this is interesting because we have to understand what are our limitations. The purpose of these lectures are not to define what is common sense, of course, but I want to develop a machinery which we understand, because we do not want to use anything like a black box. This is something which should be avoided at any cost. A machinery which will allow us to develop plausible reasoning and to study probability theory. Remember that probability theory is just an extension of logic. Now, for this, you have to get used to detach yourself from that distribution of priors, right? I'm using already some jargon, sorry, priors. Priors is a kind of, well, these are data which is populated in your head and which you use to derive conclusions which might be true or wrong. Of course, because all of us are provided with common sense, some of us less than the rest of you, we can come up with a conclusion which most of the times is quite accurate. But what I want to do is a dissection of that process, or at least of the fundamentals of those processes, because that will allow us to investigate things which are not as usual as our daily life, and for which you do not have that prior data stored in your head. You don't have a common sense for the phenomena happening in the interior of a black hole. You don't have the intuition about the probability laws which govern and describe quantum mechanics. Therefore, we have to go back to the mentality of a child and try to analyze what goes on in this process step by step. So, for this, we're going to introduce, because we are children, we're going to introduce a kind of algebra. It's an algebra which will allow us to perform quite complex operations with propositions. Remember that I will be using capital letters for propositions in a rather trivial way. Now, this kind of algebra is called a Boolean algebra. Boolean algebra. And of course, it's called a Boolean algebra after George Boole, 1850 what? 54, I think. Well, Boole did not develop what I want to see here, the symbolic logic. The principles of deductive logic were well understood many centuries before Boole was born. Now, what Boole did was to introduce a notation which will allow us to deal with problems which are very complex in a rather trivial way. Okay, so let's consider the following two propositions, A and B. A can be anything. It can be, for instance, I like eating chocolate. And B can be, I don't know, I have fallen in love with a girl. They do not have to be related. They are just two propositions which are true. Okay? Now, I'm going to denote AB. The logical product or the conjunction, and I hope that this rings a bell, of these two propositions. And it must be read as both A and B are true. Which means that I like eating chocolate and I have fallen in love with a girl. Poor girl. Now, the order, of course, does not matter. A times B, or the logical product of AB, is the same thing as BA. On the other hand, the expression A plus B, and don't get fooled again, because remember, this is just a convention. The sum of these two propositions is the logical sum or disjunction. And again, I hope that this rings a bell. This disjunction. I said don't get fooled, etc., because remember that this is just notation. I could have written something like, I don't know, this. Okay, but I'm going to use Boolean algebra. And this is a symbol that we use in Boolean algebra, this plus thing. So AB is the logical product or conjunction, and A plus B is the logical sum or disjunction. And what is a disjunction? Well, we have seen this before. It means that at least one of the propositions, A period, colon B, is true. So at least one is true. Remember the inclusive and exclusive thing? Well, it applies here as well. Okay, now given two propositions, A colon B, this colon thing is extremely confusing because I say comma in many different languages. So given any two propositions, A and B, what can happen is that one of them is true if and only if the other is true. In that case, we say that the two propositions have the same truth value. Okay? Well, this might be extremely simple because A could be, I don't know, I am in love with a girl, and B could be, I have fallen in love with a girl. Or it might be that you need a very intense and difficult labor to prove that the two things are actually, well, the one thing is the necessary and sufficient condition for the other thing. Now, at this point, we get to the first axiom of plausible reasoning. So this is going to be an axiom, Axiom One. So, two propositions, A, B, with the same truth value, are equally plausible. Now, you must agree with me, because if you do not agree with me on this axiom, we cannot move on. But it looks quite obvious and sensible. So I'm going to assume that you said, yes, I agree with you, because again, remember, this axiom thing is a kind of agreement between you and I so that we can move on. Now, this looks extremely simple, right? And trivial. And we should not even mention it. But the fun thing is that Boole himself made an error on this point in his first book. And well, he identified two propositions which were actually different. And then he failed to see any contradiction in their different plausibilities, although he later fixed that. But anyway, this is a fun point. Now, in Boolean algebra, the equal sign is used to denote not equal numerical value, like 1 plus 1 equals 2. No, don't read it like that. And again, this is just a symbol. I could have introduced something like this. Well, this would be a gamma, but I don't know, something like this. When two propositions have equal truth value, we will write that like this. Or if you want, it's up to you, like this. This means that A and B have the same truth value. Okay, now, how do you deny a proposition? Well, a proposition, or the denial of a proposition, we use a bar for it. A bar means or has the same, well, we're going to use this symbol to denote equals by definition. So A bar is equal by definition to the proposition A is false because full stop. Now, what is the relation between A and A bar? Well, the relation between A and A bar is that the two of them have the same truth value if A bar is false. So this proposition and A have the same truth value. Now, you must be careful because the bar must be can be tricky. For instance, as we have introduced, AB bar has the same truth value as AB is false. You must agree with me, right? Because I could define C to be AB, and then C and C bar would have the same truth value as C is false. But the logical product of A bar and B bar has the same logical truth value as the proposition both A and B are false. Okay? So because of this, we can see that AB bar has the same truth value as the disjunction of A bar, B bar. So the conjunction of AB bar has the same truth value as the disjunction of A bar, B bar. And it is obvious to see why. Remember that the negation of OR, that the negation in logic turns an OR into an AND, and an AND into an OR. Now, with these understandings, now we can introduce some basic identities, which I'm going to summarize now. The first thing is idempotence, which is obvious. The logical product of A times A has the same truth value as A. I am in love with a girl times I am in love with a girl has the same truth value as I am in love with a girl, right? And the disjunction of the same proposition, A plus A, so at least one of them is true, again has the same truth value as the proposition itself. Now, commutativity. We have already mentioned that A times B equals B times A. This is the short way of reading this aloud. But I urge you to practice that vocabulary. Here what I have written is that the logical product of the propositions A and B has the same truth value as the logical product of the propositions B and A, or, what is equivalent, the conjunction of the propositions A and B has the same truth value as the conjunction of the propositions B and A. This is the way you read it. And the same thing with the disjunction. A disjuncted, I don't know how to say that in English, but anyway, A plus B equals B plus A, and this is obvious, right? Associativity, A times B times C equals AB times C equals, of course, A, B, C. And A plus B plus C equals A plus B plus C equals A plus B plus C. Distributivity, my goodness, is A times B plus C equals A times B, plus A times C, and A plus B times C equals to A plus B times A plus C. And then we come to duality. Duality is the following. If, oops, this is some ads. Okay. Duality. Now, if the proposition C is the logical product of A times B, then the denial of C, as you can guess, is A bar plus B bar. So something which was a conjunction becomes a disjunction. We know why, right? An OR, so the denial of an OR is an and the denial of an and is an OR. And if following the same line of thought, if D equals A plus B, so the disjunction of two propositions, we calculate the denial of that proposition, turns out to be the conjunction of the denials. Okay. Now, it is very interesting, and with this we'll finish today's lecture. It is very interesting to evaluate what implication means. Implication. Now, implication. All of you know this kind of statement. A implies B, right? Now, you read this as A implies B, but this does not tell you that either A or B is true. What it is telling you, the only thing, and please listen to my words, the only thing that this is telling you is that AB bar is false. The conjunction of A times the denial of B is false. Now, This can also be written as the logical equation: the proposition A has the same truth value as the conjunction of the proposition A and B. Okay? So, given this, if A is true, then B must be true. Or, if B is false, then A must be false. And this is, what is this? This is the apodexis, the strong syllogism. This is what we're looking at here. Now, on the other hand, and we have mentioned this already in the other lectures of logic, if A is false, this equation is telling us nothing about B. I could tell you, crows fly, therefore that girl will also love me. Well, my chances are very low, because I don't know nothing. It could be true that she loves me, it could be wrong, it could be false that she loves me. We don't know anything, because cows do not fly. Now, the point is that weak syllogism is misleading. Plausible reasoning, the theory of plausible reasoning based on weak syllogisms, is not a weakened form of logic. It is actually an extension of logic with new content. Now, the important point, and again please pay attention. In ordinary language, in our daily life, A implies B would mean that B is logically deducible from A. But in formal logic, what we're doing here, A implies B means only that the propositions A and AB have the same truth value. This is the only thing that this equation is meaning. Now, it turns out that the choice of implication is a very bad choice. And this is actually not emphasized, stressed out in the conventional introduction of logic. And with this, I will finish today's lecture, and we'll keep on talking about this very soon.